Everybody, we'll have today Boaz Nadler from the Weizmann Institute. He'll be talking about unsupervised ensemble learning. Thank you, Boaz, for coming.
Okay, thank you, Jonathan, and thank you, Tamir, and thank you all for coming. It's great. I always enjoy coming here to the Technion. And today I'll tell you about a project that we've been working on for 5-6 years, and we're still continuing to work on it. So there are several co-authors, several works. I'll mention primarily Yuval Kluger from Yale University, Yale Medical School, who motivated much of what I'm going to tell you. And the actual title is How to Make Good Decisions When You Know Almost Nothing. Okay. All right. So this is a machine learning seminar, so I was told. So what do we try to do in machine learning? We try to construct a good algorithm that would predict well. So let's think about a binary classification problem. We have some instance space X. It can be images, strings, I don't know, features of blood results or whatever. And there is a binary output Y. And of course, our goal is to construct a classifier with good generalization, low risk. And the typical way it's done is supervised. You acquire some labeled training set, and there are many different methods to construct classifiers. And for most of them, there's a well understood theory. There's nearest neighbors and SVM and kernels. And in the last few years, neural networks are very popular. And because one can construct so many classifiers, you can think about a setting where m different people constructed a classifier. Tamir constructed the classifier, I constructed the classifier, Jonathan constructed the classifier, etc. And each one had maybe its own training data, each one had its own assumptions, design principles, etc. And in this setting, there are two key questions. One is to rank them. You would like to find the most accurate classifier. And the other is somehow to combine them to an even more accurate meta-classifier or ensemble learner. And again, the typical way you either rank or combine classifiers is in a supervised setting. You have labeled data aside. And how you rank? Well, you just apply your classifiers to your validation set. You see how well they do, and you can check who's statistically significant, more accurate than others. And in terms of combining classifiers, there are many different methods: bagging, boosting, etc. Again, all of these work in a supervised setting. So I'm not going to talk about all of that today. What I'm going to talk about today is a setting where there are m classifiers or experts, and I have a huge test data, and I can apply my classifiers to this test data. So I have a matrix of predictions, and given only this matrix of predictions, I'd like to rank the classifiers. I'd like to find who's the most accurate or who's very inaccurate, and I'd like to construct a more accurate meta-classifier, okay? And I want to do this without any label data whatsoever, okay? So again, just so the setup is clear, we have instances x1 up to xn, and we have experts or classifiers f1 up to fm, and what I'm given is this matrix of predictions, fi of xj, binary matrix, and what I would like to know are two things. I'd like to know some accuracy parameters of each of these classifiers, and to each instance there is a ground truth, which is y1 up to yn. So what's in blue is what I would like to know. It's unobserved. I only observe this matrix. Okay, that's the question. Okay, so, but before that, let me give you two motivating examples. So the first one is a true story. I work in academia, and once a month I get some salary. My wife takes most of it. This is a true story. It's photographed. It's filmed, actually. And she gives me a little bit of money aside, and I want to invest in the stock market. And for them, in the US, you have S&P 500 has 500 stocks, actually a bit more. And I don't know anything about the stock market, but I can look at advice of different entities. For example, I can ask Tamir, and Tamir tells me you should buy Intel and sell Microsoft and buy Procter & Gamble and sell, etc. I can also ask Shai, and Shai tells me, no, you should not do what he's saying. You should actually buy Broadcom and sell Intel, etc. And you can also ask your mother-in-law and your friends, etc., and your professional banker. So you really get this matrix with different analysts or experts, investment houses, and each one has its own recommendation about the different stocks. I don't know anything about the reliability of these entities. So the question is whether, given only the recommendations, I don't want to go to past data and try to see what did they say 2 years ago or 5 years ago. It may not, if it is an investment house, it may have been a different analyst. So given only this matrix, can I find out who's the most reliable advisor, and can I somehow combine their conflicting advice and get a more accurate prediction? Okay. A more scientific motivating example, and this came out of the joint work with Yuval Kluger, is the following. So first of all, if you're interested in looking at challenging large data sets, there is a website called the DREAM, which is an acronym for Dialogue for Reverse Engineering Assessment and Methods. It's a website where you have organizers of challenges, mostly related to biology. There are ongoing competitions. And you can download data, upload your solution. Typically, the competitions have several stages, etc. I'll discuss one example of a challenge that, when we were doing this work, we participated in part of it. And here the challenge was as follows: you have long DNA strings. It's not the whole. It's not the whole genome. It's certain parts, but it's orders of about a million in length. And the goal was to develop accurate algorithms to detect regions in this subpart of the DNA that are irregular, have related either to disease or to cancer. And one approach that some computational biologists apply is just, there are tens of different algorithms out there. You just apply all of them, and somehow you can try to combine them. And many of these algorithms, each was developed by its own, by a separate lab, sometimes using their own proprietary data, sometimes employing different biological knowledge or design principles, etc. And I'll show you some results on a specific challenge that we participated later on. Okay, so again, the key question here is, again, here is the DNA string, n is about 1 million, and I had about 100 different algorithms, and I had a matrix 100 by 1 million with the predictions of these different algorithms. I didn't know the ground truth at the time, of course. And the question is, can I somehow, just from such a matrix, detect who's most accurate of these algorithms and somehow combine them to get a more accurate prediction? Okay. So what's common to both examples is that we're given the predictions or recommendations of multiple advisors of unknown reliability. We have no labeled data. Either it's difficult or expensive to obtain right now, or either we'll know it only in the future. And this setting appears in several other applications. There's a whole field of decision science, which is about how to combine multiple expert advice. This is what happens in crowdsourcing. In medicine, sometimes you need to combine the predictions of different experts, etc. And a little bit about prior work. So first of all, in terms of trying to get the Y, one of the most common things is just majority voting. We're a democracy. Next week, hopefully, 6 days from today, we go and vote. Now, this is what we do in democracy, and my vote has the same weight as Tamir and others. For machine learning, this is highly suboptimal, because if one expert is far more accurate than the others, giving all of them the same weight is not the best thing to do. There's a very nice paper by Maurice de Groot with the Bayesian approach, where the different experts sit on a table, and there are multiple rounds. Each one tells each prediction, here's the prediction of everybody else, and eventually they reach a consensus. And what I will discuss today is strongly related to both this paper by David and Skin and to a spectral approach by Karger and co-authors from MIT. Okay, so what I'm going to show you is a very simple spectral analysis of this problem, essentially a method of moments. I'll make one assumption. I'll cheat you twice or 3 times, you'll have to catch me, okay? But one assumption, and I'll show you that with this one assumption, this matrix will have a very simple low-dimensional structure. Later on, we'll relax this assumption, which is quite stringent, and still will show that we still have a more complicated, but still not too difficult, not too complicated method, and we'll still develop a spectral method to do so. And this will allow us to rank the classifiers, construct a meta-ensemble learner, and I'll show you some results on some actual data sets. Okay. To be mathematically precise, as we discussed, we have a binary classification problem, an instance space X, output space Y. I'm thinking about pairs X, Y as random variables. They have some probability distribution, which I don't know. I don't know also the marginals. A binary classifier is just a function from the instance space to Y. Because it's a binary classification problem, there is a 2x2 confusion matrix, and when I assess the accuracy of a classifier, there are essentially 2 quantities. One is the true positive rate, it's called sensitivity in some literature, and the other one is the true negative rate, or specificity. And when we assess how accurate is a classifier, one option is just to look at the error rate. But if a problem is unbalanced, let's say if 70% of instances are +1 and only 30% are -1, I can always say +1 and I'm 70% right. So that's not so informative. So a common measure, it's called balanced accuracy. You just average these 2 quantities. And of course, if the problem is balanced, then this is also the standard accuracy. Okay? It's a common measure in the presence of class imbalance. And I'll show you in a minute how this quantity will naturally appear in our setup. Okay. So, again, the problem setup, I'm assuming that these x's are independent, identically distributed from the marginal of x. F1 up to Fm are an ensemble of classifiers. I don't know how they were constructed. I don't know anything about their accuracy. I only see their predictions. And I only see this matrix, and I'd like to find out the specificity and sensitivity of each classifier, and eventually also construct a more accurate prediction of the y's. Okay? So I want to rank them, combine them, and do all of that without any labeled data. Okay. Now, clearly I need to make some assumption. Otherwise, for example, if all of these are just random, so this matrix is just random, has no information about y, I won't be able to do anything. And the assumption I'm going to make, it's a standard assumption in both statistics and machine learning. It's called the conditional independence. It's an assumption that has also been made in supervised ensemble methods. The assumption is that, well, it's one equation, it's the following one. The assumption is that each classifier has its own accuracy parameters, and they don't talk to each other if you wish. They make statistically independent errors. Okay? So the probability that classifier I and classifier J give as outputs AI and AJ is just the product of the individual probabilities. If I made an error, it says nothing about the error that Anat will make. Okay? This is in the context of crowdsourcing or ensemble learning. This is called the Weed and Skin model, but it goes much earlier, at least to the 1950s, in the psychometric literature. Okay, it's a very simple graphical model. There is a hidden latent variable y, and what we observe are, so for each x there is a hidden variable y, which is its label, and given the label, each classifier outputs its prediction according to its own accuracy parameters. Okay? All right. So, yeah. Okay. So, let's see if under this assumption, put it here, can we find out which row, which classifier is most accurate, which one is just totally random or something like that? Any idea, intuition?
The probability is over x, right?
This probability is over both, yeah, well, it's conditional on y. Yeah, so.
Wait, but it's over x and y? Or is it for every x you make this assumption? For every sample? I'm missing something.
It's over x. Probability over x, otherwise there's no. Yeah, the f is the deterministic function. Yeah. Okay.
So, I'm sorry, so I just...
But it holds for any y, so it's the probability is over the marginal of x conditional on y. Okay. All right. Okay, so here's my matrix. Can I detect who is most accurate and who flipped the coin? Okay. All right. So any ideas?
Take the majority vote of the rest
Okay,
of
so
the
one
vote.
option is, let's say, first compute the majority vote of everybody, and then...
I can isolate one of the rows and take the majority vote of the rest of the rows.
Okay, so if I had 100 classifiers and only 5 of them were accurate and the other ones were bad, majority voting would be as bad as random, and your method would not work so well. But first, let's try. So let's assume that here is one expert, which is very accurate. Here's another expert, which is very accurate, and here is another one, which was just random. Okay. So this is me. I'm very lazy. I just flipped coins. I didn't want to waste my time constructing a classifier. So let's see if you can detect if this row, if this classifier was just random. So if this one was just random, if we look at its predictions with relation to any other row, what would be the correlation between them? Zero. Yeah, I mean, 1 over square root of n. Yeah, close to essentially 0. So that's on the one hand. On the other hand, if here we have two classifiers which were quite accurate, what would be the correlation between them? Quite high, because they are both trying to predict the truth. They make independent errors, okay, but most of the time they agree. So now I don't have to do that. So I can actually look at all m squared correlations, and maybe from that I can extract some useful information.
But the correlations would also be high if they're both consistently wrong, right?
But this is precluded by this assumption. Okay, but I'll get to your point later on. Okay. All right, great. So indeed,
Fake estimates.
what?
These are fake estimates. Like fake news.
Yeah, I'll get to that in the second part of the talk. Yeah. because this assumption may not always hold. Yeah, exactly. Okay, so indeed, what I just told you, what motivated, maybe we should look at the covariance matrix between all the different classifiers. Here's its definition. And here's a lemma that we proved in this work. It says that in the population setting, when n goes to infinity, this matrix, this covariance of the classifiers, has a very simple structure. There is something on the diagonal. We don't care about it for the moment. But look at the off-diagonal entries. B is the class imbalance. So if a polynomial is balanced, B is just 0. And pi, if you remember, was the balanced accuracy of the classifiers, okay, which naturally comes here. So now, simple linear algebra for students. If I have a matrix R, which is rank 1 and it is symmetric, then it has the following form. It's just V times V transpose, right? In other words, a rank 1 matrix, its ij entry is Vi times Vj. And what's written here is that this covariance matrix of the classifiers is a rank 1 matrix. Okay? Now, rank 1 matrices, how many eigenvalues they have which are non-zero? 1. And the eigenvector is V. So, here is a way to rank the classifiers. Construct the covariance matrix. I need to correct for the diagonal. Let's put that aside for a minute. Compute the leading eigenvector. Sort its entries. Now the leading eigenvector is going to be proportional to the balanced accuracy. So you can sort its entries from largest to smallest. And the largest one is the most accurate classifier. The smallest one is the least accurate. And you're done. So linear algebra, eigenvalues, I was able to program this myself. Okay? This idea is also stable to the fact that I have a finite amount of data. I don't have the true covariance matrix. I can only compute the sample covariance matrix. Again, I need to correct for the diagonal. This is a technical thing, so it's not so important. But as I've said, I can compute the leading eigenvector, and I can sort its entries, and I got my ranking. I fooled you, by the way. I told you I would fool you. Okay. Oh, I cheated you.
You need to know the balance.
The balance would be 2
Just-
slides later on. No, it's because
Does it
it's just a
scale?
proportionality factor, so I don't care about it. If I just want to rank, I don't care about the balance. But I still cheated you. So let's see. So first of all, eigenvectors, are they unique? Only up to a plus or minus 1 sign ambiguity. So computing the eigenvector and taking its entries and sorting them can either be the right sorting, and I'll take the most accurate classifier, or it could be the reverse. I'll take the worst classifier. That's maybe not so good. So there is a sign ambiguity. It was here. There is a plus or minus 1 sign ambiguity, which I need to resolve. And for that, I need to, for example, assume that most classifiers are better than random. In that case, most entries of V would be positive, and I will know the right sign. Okay? I cheated you elsewhere, but you didn't catch me, so I'll just proceed. Okay. So this, yeah.
So now we cannot really rely on your talk.
You should never rely on my talk. It's not local, it's a global thing, okay? Okay. Just a starting point. Okay. This spectral approach allowed you to rank the classifiers, or if you knew the balanced accuracy, it would allow you to find a pi, only the balanced accuracy. If you want to find the actual accuracy parameters psi and eta, you can also do that. It's very easy. So far we only looked at the second moment, right, at the covariance matrix. We can also look just at the first moment, at the mean of each row. And it turns out that the mean of each row is a linear combination of psi and eta. So again, if you know the balance accuracy, you have two equations with two unknowns, and you can find psi and eta. And this is a consistent method if the model is correct. As sample size tends to infinity, the sample covariance converges to the true one, and all of my estimates converge to the true values in probability. You can also do a sensitivity analysis, because each entry of the sample covariance scales like 1 over square root of n. You can show that the leading eigenvector also has an error like 1 over square root of n, also like 1 over the largest eigenvalue. And this implies that all of your estimates are rate optimal. And if all of your classifiers are better than random, then it's good to have more and more classifiers, because then the eigenvalue lambda scales like the number of classifiers, and you get better estimates of the eigenvector v. Okay? If you don't know the class imbalance, as Uri here asked, then we looked at the first moment, we looked at the second moment, so all we need to do is to look at the third moment, the tensor, and in this setting the tensor is also rank 1, with the same eigenvector v, but with a different proportionality parameter that depends on class imbalance. So you compute your third order, you estimate this quantity, you invert it, and you get your estimate of b. So everything is solved by essentially methods of moments. Again, asymptotically consistent, you don't need to do tensor decompositions or anything. Okay. Now there's an interesting relation between this work and a topic that received some attention in machine learning. It's about learning mixtures of product distributions. So when we make the assumption that all classifiers make independent errors, the problem I just discussed is essentially equivalent to that of learning a mixture of discrete product distributions, in this case of binary distributions, because each column comes from either one of two distributions, depending on the latent variable y. And one of the first papers to propose a computationally efficient method to do so was by Yoav Freund and Ishai Mansour from 20 years ago. It's a very complicated method, and I'm not sure I'm able to implement it. And in the last few years, many other people proposed other methods based on tensor decompositions. But at least in the binary case, our method is very, very simple, only requires linear algebra and matrix decompositions. And at least for the binary case.
When you say binary, where the latent variable is binary?
The latent variable is binary, and these are also binary. Yeah.
Because these methods don't assume that the latent is binary.
For some of these methods, they work on multi-class, at least this one. And they require tensor decompositions, and this for the binary case, you can get away just with eigenvalues and eigenvectors. Yeah. Okay. All right. Good. So the next thing is how to combine the classifiers. So again, we have, in principle, if we knew well, the common approach would be maximum likelihood, of course. Look for the parameters that maximize the likelihood. You can write the likelihood function, solve it, etc. And it turns out that if you knew psi and eta, the maximum likelihood would be a weighted linear ensemble learner. You have weights that they have some offset, but weights that depend on the specificities and sensitivities of the different classifiers. So if I knew everything, I would just apply this. But the problem is that I don't know psi and eta, and jointly optimizing over y's and psi and eta is a non-convex problem. What David and Skin suggested in the paper from '79 was to solve this by the EM algorithm. For example, they first do majority voting. This gives you an initial estimate for y. Once you have an initial estimate for y, you can estimate psi and eta. Then you can plug it into the weighted ensemble learner, recompute y, do this several iterations, and of course, EM, we know that it is monotonically increasing the likelihood until it converges to a local maxima, and this was widely used in many papers or variants of it. And of course, the limitation of EM is that we only converge to a local maxima. We need a good initial guess for Y, and we don't, in general, have good performance guarantees on its solution. And the question is, can we do better? When Obama was president, I would say, yes, we can. Now Trump is president of the US, and we say, let's make EM great again. And one simple idea is just, I just told you how I can get good estimates of psi and eta by a simple spectral approach, so I can use that as my initial point for EM. Or in fact, I can just forget about EM, just use that, plug it in, and get my estimate of Y. And so we call this approach SML, Spectral Meta Learner. And the question, of course, is, does it work on real data? Particularly, the assumption of conditional independence may not hold exactly. Okay. First, we played with a lot of simulated data. We just downloaded many data sets from UCI. We constructed many classifiers ourselves on part of the data, tested it, and applied them on test data, etc. And now, suppose there's no free lunch. If the assumptions don't hold, our method will not work. But there are some things that you can assess even before applying your method. For example, our method claims, or under the assumptions, the covariance matrix should be rank 1. So you can check, you can compute your covariance matrix and check if lambda 1 over the trace is close to 1. If it's close to 1, then there is hope of doing what I just told you, otherwise, מחשב מסלול מחדש. And of course, if you know the ground truth, you can check if the assumptions really hold. Let me show you one example. Everybody wants to make money. So we took data from the stock market, we took data from 9 days, and we wanted the binary classification problem, so we asked, you observed 9 days of trading, and you asked whether on the 10th date, the highest price was more than 5% than the highest price 1 day earlier. Okay, so did your stock went up by at least 5%? This is an unbalanced problem. Most stocks don't go up or down more than 5% in a single day. And let's start from this. This is, the y-axis is balanced accuracy. This is the median balanced accuracy of something like 17 different classifiers we constructed. Of course, we constructed on some years and applied it on different years, okay? This is what you get when you start EM from the, let's say, the majority voting. Most cases you get stuck at half. A few cases with this multiple time, a few cases you succeed. This is the entry with the highest eigenvector entry. It's somewhat better than half. And this is starting EM with our vector of estimated psi and etas. It's slightly better than half, okay? I'm here, I didn't make a lot of money out of this. Don't try this at home. Okay. Next, we were very happy, we applied this idea to the biological data that I showed you before. And so, for the dream data set that we were looking at, we had about 100 classifiers. I can tell you that each had an error which is less than 10%. And if they were all conditionally independent, then you can just apply a simple Hofding bound and get that this majority voting would get you an error which is less than 1 over a billion, which is not the case. So the assumption that all classifiers are conditionally independent was strongly violated in this case. So we had several data sets. For some of them we already had the ground truth when we were doing this work. And for those matrices for which we had the ground truth, we could have computed this conditional covariance matrix, which would have been diagonal, and all of the diagonal enters would be 0 if the independence assumption were to hold. And as you can see, well, in this example I had about 120 classifiers. It had a certain block structure. So this group of experts were correlated made correlated predictions, correlated errors, and this, and this, and this, and this. And I have a conjecture why is this so, because in this competition each group could have submitted several solutions. So if you have now remember, to get a solution to this problem, you start from this DNA string and you put in a lot of biological knowledge, etc. There were also other features that I didn't tell you about. There's a very long pipeline with many different knobs and parameters that you can play with. And I think that, so again, I don't know, because from my perspective, I just got a matrix with predictions, but I think that quite a few of these are solutions by the same group with slightly different parameters. Okay, if you want to win a competition and you have a base classifier, just perturb it a little bit, send in 30 solutions, and hopefully one of them would do better in your test data. So the question is, can we? So this is a matrix I compute when I know the ground truth, and the question is, can I detect, again, no label data whatsoever, that some classifiers are strongly dependent, but not necessarily accurate. Okay. So this is joint work I did with my PhD student Ariel Yaffe at the time, and we came up with a more complicated model, which has another layer with hidden variables. So here is your hidden label y. We assume there is an intermediate hidden layer of other variables alpha, and our experts are here, and experts that belong to the same teacher, if you wish, they make correlated errors, but if they belong to different teachers, then they are still conditionally independent. Okay, you can think about these as these are students. Both of these students took the same course by Tamir, and Tamir has his own views on how to construct classifiers, and these guys took the course by Uri Shalit, and they have a different way to construct classifiers. Okay, so that's the model, and the question is, I only observe that matrix. Can I infer this model, its structure? Can I somehow learn K? And the assignment, how each expert belongs to which teacher. And again, yeah, so this is the assignment function. It tells you which classifier belongs to which teacher. And again, in this model, the key challenge is to find this assignment, find the number of teachers and find this assignment, because once I know that, inference about the parameters is relatively easy. And again, we just looked at the covariance matrix. So in this model, the covariance matrix is more complicated. It's not rank 1 anymore, but it's a combination of several rank 1 matrices. Each teacher defines its own block. Within each block, you have one rank 1 matrix, and the off diagonal outside of all the blocks is a different rank 1 matrix. Okay? So overall, the rank of this matrix is higher, but
Is it exactly K?
I think it's K plus 1 or something. Because if you have two blocks, then you have rank 1, rank 1, rank 1, another one outside. Now the question is, how can we use this observation to find the structure? And the idea is to look actually at groups of 4 variables. In other words, compute the covariance matrix and look at just four of its entries. Okay, I, J, K, L. And look at its determinant. And you can show that if all 4 experts belong to 4 different teachers, this matrix is rank 1, the determinant is 0, and for many other cases the determinant is not 0 in general. And you can show that if I had perfect knowledge of Q, then by computing these determinants I would, with probability 1, infer the structure. Of course, in practice I only have an estimate of Q. The model I assumed is only approximate, and you can show that finding the best assignment function is essentially an NP-hard problem.
But without noise, though, it's not without noise, it's just...
Without noise and perfect model, unless you have degeneracy or something, it's yeah. This is sufficient. If you know the yeah.
And you need like k-squared determinants or something?
No, I'm just going to compute all of them. M to the 4th, but it's still doable because M is typically 100. If M were 1,000, it start to become more definitely, yeah. Okay, so what we suggested was just to sum for each pair I and J, just sum all of these determinants over all other pairs K and L. And again, if I and J don't belong to the same teacher, many of these determinants would be 0, whereas when they do belong to the same teacher, there are far fewer entries that are 0, and there are many more entries that are non-zero, and therefore we suggest to use this quantity as a proxy to detect when 2 experts do belong to the same teacher or not, when are they strongly correlated or not. I don't have it here, but we have a theorem that under certain conditions this suffices to separate these 2 cases.
Sell it to Facebook now, to filter the fake account.
Okay. So again, this was the conditional covariance matrix I showed you before with this block structure, and this is the score matrix that I just told you that I can compute just from unlabeled data, and you see a nice, they have similar block structure, so I can easily find which of the classifiers belong to the same group. Again, this is a measure of how strongly correlated are classifiers, and this is our score function. And again, when classifiers are strongly correlated, the score function is high. And once I have some assignment, then inferring the parameters is just applying the Darwinian model twice, once at this level, once at this level, and then you compute your ensemble learner. Here are some results. So these are on this dream data set. I had 3 different matrices, each of one each had slightly different number of experts. This is just the number of participants that submitted solution, and each matrix was around 1 million columns. Here I'm showing you for each of these matrices what was the mean accuracy of the roughly 100 classifiers. The most accurate of them, if I knew the ground truth. This is what you get from majority voting. And on the very far right, this is what you get from our latent spectral meta-learner, which assumes this tree structure. So in some cases, I get even better than this single most accurate classifier. In any case, I always get better than just majority voting. And we participated for one of these data sets, there was an ongoing competition in which we participated. We were not the very best, but we were among the top, or the most accurate group with their predictions. As I said, this data set had other features that we did not use. We just combined the predictions that were available to us.
Is it the single best classifier? Or
Yeah,
is it
this
the
is the
best
single
prediction?
best classifier in hindsight, if you knew it.
Oh, but it's not the best prediction for each sample individually, right?
No. It's, no. Okay. Everybody does deep learning now, and we had no choice. And we also did it. We just in an unsupervised way, trained stacked restricted Boltzmann machines, and then we got results that were as good as this or even better than this. But for that I have no theory, but that's life. Okay. So to conclude, I presented a very simple spectral analysis of this form of unsupervised ensemble learning. The key idea was to exploit this low-dimensional structure of low-rank matrices and tensors. What we're currently doing is unsupervised ensemble regression. In other words, when y is continuous, all of these are continuous. Accuracy, you can maybe measure it by mean squared error or something else. And there are many other topics, some on which we're working on, and some others are just wide open. So one of them is semi-supervised. What happens if you know the labels for few of the instances, and you also have a lot of unlabeled data? We have some work on understanding what is the value of labeling. There are cases where labeling is very, there are settings where labeling just a handful of labels is very, very beneficial, okay? Particularly when many of the experts are weak. You can think about other models, for example, models that have instance difficulty. In other words, think about the instances as some very easy to predict the true label, and some it's more difficult to predict the true label. You can also think about sparse ensemble learners. You have maybe hundreds of experts, but you just want to use 5 of them. It's not necessarily the 5 which are most accurate, because if they're strongly correlated, it doesn't give you much. Actually, you want them to be diverse. There are some real applications that we're working on. One of them is related to earthquakes, where different sensors around the world measure the same earthquake, and you want to combine their predictions. And there are various papers that are on my website, and I'll finish here.
Questions from anybody?
Thank you for the talk. I'm wondering about multiclass. Actually, you can think about multiclass as one versus all, and have a K analysis.
Yeah. So actually, I didn't talk about it, but So Tamir asks, what happens if y is one of, let's say, 5 classes? Now, instead of just having 2 parameters, you have a 5 by 5 confusion matrix, right? On the diagonal, you have the accuracy for each class and the confusion everywhere else. Our method assumes binary, so as you say, you can do 1 versus all, or any subgroup versus any other subgroup. 1 versus all allows you to compute what's on the diagonal and the sum of the off-diagonal entries. If you do other combinations, you can get other linear combinations of some of the entries. What we proved with my student is that you cannot fully solve this problem, at least in the worst case, by reductions to 1 versus all, because there's not enough. I mean, I can construct confusion matrices that they cannot resolve their entries by reductions to 1 versus all. Okay, so there is a price to pay for this simplicity of binary problems. The papers I mentioned by Anand Kumar and others, they solve the multiclass, but that requires tensor decompositions. It's far more complicated, and it's, for my limited experience, it's much more sensitive to noise than lower order methods. Yeah.
Is there some, I guess, lower bound or something to estimate what is the level of assumptions you need to get some information, like a tree structure you assumed in the end? Is that necessary, or is there some lower level assumption you can do? Insight on that?
Well, the three assumption I made is just an approximation. It was motivated by what we saw in that dream data set. It may not hold, and you may need to assume something else. I don't have a deterministic answer to your question.
No, let me ask some insight. Maybe you said if it's completely random, then you can't improve. But is there some basic property that you need to have in order to improve using unsupervised ensemble learning?
Well, the basic property you would need is that you need some of these experts to be correlated, to be informative of the ground truth. I think that if only one of them is related to the ground truth, that would not be sufficient because you wouldn't know which one. So this is where I cheated you to begin with, since you raised it. So in the first part of the talk, I said that I'll compute the covariance, I'll compute the eigenvector, etc. But if you recall, in my matrix, the diagonal entries are not informative, they're not rank 1, and only the off-diagonal are rank 1. And so for example, if you only have 2 experts, you only have a single informative entry, and you have 2 experts. So you actually don't know who's more accurate, and if you have only 2, so you can show that even for the simple model, you need at least 3 experts which are non-random. Okay? So that's where I also cheated you. So thank you for asking the question. So, he said he left because he said, yeah, I couldn't be trusted, so maybe I can be trusted. Okay, yeah.
If you find the matrix to be low rank, like what other assumptions do you need to add to that in order to be able to make some inference?
Well, the matrix can be low rank and all of these. Think about
it could be low rank and junk, sure. So you need to have something.
No, not junk. Think about investment houses, and they were invested in some stocks, and they will tell you actually to buy the stocks that they were already invested, regardless of the ground truth. So the fact that the matrix is low rank does not imply that any of these.
No, you need at least you need at least some assumption that at least some of them are good, right?
Yeah.
Or at least one is good. But
And not
is that enough?
3.
3.
Yeah.
That's like the Spearman 3 independent peaks.
Yeah. 3 is the minimal number for identifiability of this model. Okay.
But if you assume that you have at least 3 views, it's low rank, and at least one of them has some positive value.
No. You need 3 that are non-random. If you think about 100, but only 1 is accurate, you don't know. You can't find. You can find it. So even in my tree model. Again, I need. It's an open question. What are minimal assumptions that you need to make in order to solve this problem? I don't think there is a definite answer. Yeah.
So if you have more people that tell you with a bad purpose and assumption, more experts that they tell fake news.
Okay. Yeah.
So you will go for them.
Exactly. So in our original paper, we called it cartels, and that was way before the fake news. Not surprisingly, we assumed that the size of the cartel was less than half of the number of non-random classifiers. Otherwise, you don't know which one. If you have 2 groups, some of them are telling you to go that direction, some are telling you to go that direction. You need the people who are right to be.
But is this robust to adversarial? If I know all the other m, could I add an m plus 1 and flip you over?
It's robust to few adversarials just because spectral methods with binary are robust. Yeah. There have been a few works on adversarial crowdsourcing. I haven't analyzed the precise robustness to adversariality in my model. I didn't encounter adversarial experts in the datasets that I played with.
Sure. But in the stock market, you might. Who knows?
So, yes, in investment houses, you can definitely get adversarial experts. Yeah.
So let's thank Boaz.
Okay.